Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I have designed the internal stability, or I have checked the internal stability of an reinforced retaining wall under static condition, and I have decided the length and the spacing of the reinforcement. And so, today I will continue that design procedure, and I will check the external stability, and then I will incorporate the seismic load or load due to earthquake. So, now you can see that the spacing was not uniform throughout the depth, but I have provided a uniform spacing of 0.25 meter center to center, and based on that we have total 16 number of reinforcement, and the placing depth of those reinforcement will be 0.25 meter, 0.5 meter, 0.75, 1 meter and 4 meter, and we can calculate the LE and LR at all the depths, and you can see that L will be maximum at top, okay, that at z equal to 0.25 meter, and that is 2.95 meter, because here LE is greater than 1, because LE is coming out to be 0.28 meter, and which is less than 1 meter, but I have to provide 1 meter, so that's why I am providing LE is 1 meter. LR is coming 1.95 meter, so it will be total L will be 1 plus 1.95 meter, 2.95 meter, but at the 4 meter it is required L is 1 meter, but I am providing the 3 meter throughout the depth, and I have already discussed why I have taken only 15 not 40, because your dead load will present always but not the live load, and if I provide 40, then required LE will be, your required LE will be less, because you are dividing it by 40. So, that means required LE will be less, but when this live load will not present, then the required LE will be more. So, that is why, to be in the safe side, I should not consider that live load surcharge here. But here the required LE is 0.28 meter. So, even if we have utilize the 60% of TL level, but that is why we have taken the minimum required LE, that is 1 meter. So, now let us check the external stability of the your system. So, my trial 1, say, so it is I can say this is my reinforced zone. So, length is 3 meter, and this is your height is 4 meter, okay, and there will be surcharge, and that surcharge 15 I am considering for the live load plus 25 kilonewton per meter square. So, that 25 kilonewton per meter square is for live load, and 15 kilonewton per meter square is for dead load, and your unit weight is 19 kilonewton per meter cube. So, this is our all the dimension, and your PA will act here, which is at a height of 4 by 3 meter. Okay. So, I can calculate that PA, that is equal to half into gamma, here it will be gamma field, okay, and Ka will be for, which is you have to consider phi field, remember that, because here this PA is acting in this side. So here this will be Ka, you have to calculate with phi f, but here phi f is equal to phi r, that's why we can use the same Ka, but remember that if they are different, you have to use the phi f, because this is phi r, this is phi f for fill, and this is the reinforced zone. So this is your H square. But here the values are same, so that's why I can write this is also 19 into 0.27 into 4 square. So that is 41.4 kilonewton per meter. This is due to the weight of the soil, okay, this is weight of the, or I should say this is due to the backfill soil, surcharge, the PA due to the backfill soil, okay. Now there will be another PA that is due to the, or you can say this is PA dash, this is due to the surcharge. So that is equal to your 40 into 4 into 0.27. So 40 is the surcharge, 4 is the height into 0.27, okay, into 4. So it will be your 43.2 kilonewton meter. And that is, this is PA, and that PA dash, that will act as a height of, say, your 4 by 2 meter, okay. So this is your PA and PA dash. So now the total vertical force will be how much? That will be your 4 into that your V or W, that is equal to 4 into 3 into 19, that is the weight of the reinforced zone, plus 15 into 3. Again I will discuss something. So that is equal to 273 kilonewton per meter. Again in case of your PA calculation, I have taken 40 as the surcharge, but in case of sigma V calculation, I have taken 15 as a surcharge. Why? Because as I was discussing in my previous lecture, that whenever the surcharge will increase your factor of safety, I will consider only the dead load surcharge, because that I cannot neglect, that will always be present. So if that will increase your factor of safety, I will consider only the dead load surcharge. But the case where it will reduce the factor of safety, then I will consider both dead load and surcharge. Clear? So now my design consideration is whenever your surcharge will increase the factor of safety, or it has a positive effect on the factor of safety, then I will consider only the dead load surcharge. But when it will decrease the factor of safety, it has a negative effect on the factor of safety, then I will consider both live load and dead load surcharge, because live load will always not be present. So that's why whenever it will increase the factor of safety, I will not consider the live load. But if it will decrease the factor of safety, I will consider both. But there is a question that if the live load is not present, then I should not consider the your PA due to that surcharge also. But this is the worst combination, that's why I will consider that. But you can, as a designer, you can decide that if the live load is only present, then I will consider both. If it is not present, I will not consider the live load effect, whether it will increase the factor of safety or it will decrease the factor of safety. If live load present, I will consider both the cases in increase and decrease. But if it is not present, I will not consider it will not in any cases. But that is the designer's decision. But here I will consider the worst condition. Okay, so if there is if the surcharge will increase the positive increase the your factor of safety, I will consider only the dead load surcharge. If it will decrease the factor of safety, I will consider both live load and the dead load to be the to be in the safe side or the worst combination, you can say, in terms of factor of safety. So here the PA dash definitely will reduce your factor of safety in stability, but sigma V will increase the factor of safety. That's why in PA dash calculation I have considered 40, but in sigma V calculation or summation of V vertical force calculation, I have taken only the 15, because it will increase the factor of safety. Clear? So now if this is the combination, then I can calculate the factor of safety for sliding. That is equal to your addition value is 40, length is 3 meter, total vertical force is 273 into tan. Now it will be base. Okay, 40. So that means I can write that here it will be CAL plus summation of V into tan delta base, okay, divided by summation of H, all horizontal forces. So here the summation of all horizontal forces, it will be 41.4 plus 43.2. So you can see that here why I have taken only 15, because this sigma V summation of V is increasing your factor of safety, but this PA dash, this is your PA dash, that is actually reducing the factor of safety. So that's why wherever it is increasing the factor of safety, I will consider only the dead load surcharge. Wherever it will reduce the factor of safety, I will consider your live load and dead load both the surcharge, because if it is the increasing or factor of safety, there I cannot consider the live load, because live load will not present all the time. Okay, but as I mentioned, as it's a designer choice how it will do that, but I have considered the worst condition, so that's why. So now it is your coming out to be 2.22, which is greater than 1.5, so it is safe. Now go for the factor of safety for overturning. That is your so resisting moment and the overturning moment. So your resisting moment will be 4 into 3 into 19. This is due to the weight of the reinforced zone into the momentum. Momentum will be 3 by 2 if I take with respect to toe. Okay. plus due to the surcharge, and again here I will consider only 15 because it will increase the factor of safety, into 3 by 2 surcharge divided by the overturning moment, that will be 41.4 into 4 by 3 plus 43.2 into 2, 4 by 2. So, it will be equal to 2.9, which is greater than 2 safe. So, my resisting moment is coming out to be 409.5 kilonewton meter per meter, and overturning moment is 141.6 kilonewton meter per meter. Okay. So, I can write that x will be, okay, so I think there is I have multiply one extra 4, it will not be there. Just check it. So, I have multiplied one extra 4, it will not be there. I have already multiplied the 4 because your sigma h will be 40 into 0.27. Then I have to multiply the 4, that will give you the total lateral force. Okay. So, it is kilonewton per meter square into 4, it will be kilonewton per meter. So, I have multiplied one extra 4. So, that please note that. Okay. So, now it will be 40 into 4 into 0.27. It will be 40 into 4 into 0.27. So, now come back to that x calculation. The x will be summation of mr minus summation of m0 divided by summation of v. So, it is coming out to be 409.5 minus 141.6 divided by 273. So, it is 0.98. Okay. So, E will be B by 2 minus x bar. So, it will be 1.5 minus 0.98. So, it is 0.52 meter. Okay. So, which is almost close to the B by 6, which is 0.5 meter. So, which is almost close. So, I can say it is your safe or slightly or marginally safe. Okay. But E you can calculate another way also. E you can calculate, just put your m0 divided by summation of v. This way also you can calculate the E directly, or you can calculate, first calculate the x, then you calculate the E value. Okay. So, now for the bearing calculation, what I will do? So, that means this is also marginally safe. Now, for the bearing calculation, when I will calculate the summation of V, then I will take the dead load and live load both the surcharge, because it will reduce the factor of safety. Na? So, here when I calculate the your x E value, then I consider only 273. Okay, because if I consider the 40 kPa, then it will further reduce the E value. Clear? So, now if it is your bearing calculation, then I will consider your, here I will consider 4 into 3 into 19 plus 40 into 3. Okay. So, it will be 348 kilonewton per meter. Okay, and Q I can calculate by this equation, that summation of V divided by your B minus 2E, because Q I can calculate this way also, because here your, if I divide by B, then the full area of the base is considered, but now due to the eccentricity your effective width of the foundation is been reduced, and that this is the effective width of the foundation. So that's why I am taking B minus 2E, that is the effective width. So now if I put this value 348 divided by 3 minus 2 into 0.52, that means that E value I am taking, though it is marginally safe, remember that. So it will be 178 kilonewton per meter square. And my another thing that I didn't give you, that my Q allowable of the base soil is 200 kilonewton per meter square. So this is for base soil. Okay, it is giving 200 kilonewton per meter square. So now it is less than 200 kilonewton per meter square, so it is safe. So that means under static condition it is safe. Okay, but you remember that you have to check two more conditions. One is the settlement of this total reinforced soil. So that settlement check you have to do it, because you have to see that whether the your foundation there is no excessive settlement. But as it is Q is given Q allowable, that means it is expected that in this Q the bearing consideration and the settlement consideration both are given. That's why it is Q allowable. That means remember that the settlement also you have to consider when you calculate the Q allowable. Obviously Q allowable means it is the minimum of the stress that can take the soil, considering the bearing as well as the settlement. That means settlement is also another thing that you have to check, that I want to mention. Another one is you have to check the global factor of safety for slope stability. That means here you have to check the global slope stability checking. So it will so that also you have to check, and we assume that these are safe. So that is we are doing the our traditional reinforced retaining wall design part, but in addition to that, bearing, settlement, this global factor of safety, those we have to check. Okay, so and remember that when you calculate Q allowable, that means it is the settlement is also considered. Okay, that means settlement check is done. So that means this is under static condition, this is safe. Now I will consider the seismic load. Consider seismic load, because it is A max by G is given 0.24. So I will calculate AC by G, which is 1.45 minus A max by G into A max by G. So it is coming out to be 1.45 minus 0.24 into 0.24. So it is 0.29. Okay, so now if I draw the reinforced zone, this is 3 meter, this is 4 meter, Okay. Now we have taken a failure surface, that angle is 45 minus 5 by 2, and there is the reinforcement. Okay. These are the reinforcements. Because I have taken the uniform reinforcement and there is another reinforcement here. And so on. Okay. Now this failure surface, this is H, this is 45 degree minus 5 by 2. So now I can calculate what is this value. So this value is at 2.1 meter. Okay. This value is 2.1 meter, which is very easy because I know this is 45 degree minus 5 by 2 and this phi will be phi r. Okay. And this angle also I can calculate. So I know this height, I can calculate this length. This is 2.1. Similarly, the length, so this is the your LE dash, the length beyond the failure zone for this reinforcement, it is 1.05 meter. That also you can calculate because this one is 0.25 meter, because this is my first layer, that is 0.25 below the top, and this one is 1.25 meter. Second one is, this one is 1.18 meter, and the last one will be, this is 0, the last one will be 3 meter. Okay. Now what I am calculating? I am calculating the PIA, because I have given the expression of PIA. PIA expression is half into H into L dash into gamma R. Okay. That is the weight into the AC by G. That is for this weight, but for surcharge is there. Now surcharge, because of the surcharge will be 40 into L dash into AC by G. So this contribution is due to surcharge. This contribution is due to weight of the reinforced zone or the failure mass. Reinforced zone, failure mass, not the total reinforced zone, only the failure mass. So here also, as this force I have to consider and I have to distribute in the reinforcement, that's why it is taken 40, not 15. It is taken total surcharge. So that means how it is been calculated, this is the weight of this failure mass into that acceleration. Okay, and this is also your weight due to surcharge, that is 40 into L dash. Here L dash is 2.1 meter. L dash is 2.1 meter. The surcharge also will be considered. So now the final load will be half into H is 4 into 2.1 into 19 into 0.29. Plus 40 into 2.1 into 0.29. Okay, because this is weight, remember that this is weight and our this mass into acceleration. So that's why W by G, and it is into acceleration. How it is coming? it is coming, this is W is this value, this is divided by G into acceleration. So that's why I am writing it is W AC by G. Okay, why? Actually it is mass into acceleration. So now this PIA value is 47.5 meter. 47 kilonewton per meter. Kilonewton per meter. Now that is the force developed in that failure zone, and that force, who will take this force? The reinforcement will take this force. So I have to distribute this force to the reinforcement. How I will distribute that? As I mentioned in my previous lecture, that will be proportionate to the resistance area of the reinforcement. So how I will do that? Let calculate that. So now for I have total 16 reinforcement, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now the proportionate area, what is the your LE dash? LE dash. LE dash means this extra zone. Resistance area will be the area beyond the failure surface. So this is my failure surface. So this one I have to consider for all 16 cases. So for the first layer it is 1.05 in terms of meter, 1.05. Total is 3 meter, and this area it will be slightly less than 2.1, it will be around 2.05. So this will be 1.95. This is 1.95, you can calculate, and this is 3 minus this. This is 3 minus this is say 1.95. This will be 1.95. This is 1.05. So total will be 3 meter. Okay. So you can see this is 3 meter. So similar way I can calculate what is the length of each reinforcement layer beyond the failure surface. So now for the second layer it is 1.18 meter. So it will be 1.18 meter. And for the similar way I can calculate for third layer it is 1.31 meter. Then it is 1.44 meter. 1.57 meter, 1.7 meter, 1.80 meter, 1.96 meter, 2.09 meter, 2.22 meter, then 2.35 meter, then 2.48 meter, 2.61 meter, 2.74 meter, 2.87 meter, and this will be 3 meter. Because the last one, the length is 3 meter. So that means the maximum force will be distributed to the lower reinforcement because it has maximum amount of area that is giving the resistance. Okay. So that means how I will do that? First, do a summation of all the lengths. So summation of all the lengths is 32.4 meter. So this is the case when my length is 3 meter. That is first trial. Now I will distribute it in this way, that this will be, how it will be distributed? This will be distributed by your that this force will be distributed by, this is your the P1A, then LE dash divided by summation of LE dash. Okay, or if I write these things this side, how the forces will be distributed? The forces will be distributed in the each reinforcement layer Ti, that is the developed tensile force in each reinforcement layer due to seismic force. Okay, so this will be equal to P IA, then LE dash summation of total LE dash. Okay, so now for the first layer, what will be the TI will be developed for the first layer? For the first layer, TI for the first layer, this will be total is 47.5, then first layer it is 1.05 and summation is 32.4, so it will be 1.54 kilonewton per meter. Similarly for the second layer, it will be 47.5 into 1.18 divided by 32.4, and similarly for the 16th layer or the last layer, it will be 47.5 into 3 divided by 32.4. So last layer it will be maximum, it is 1.73, then it is 1.92, then it is 2.1, then it is 2.30, then 2.49, then 2.68, 2.87, 3.06, 3.25, 3.45, 3.64, 3.83, 4.02, 4.21, 4.44. So if I add them, it must be 47.5. Okay, must be 47.5. So that means here it is 1.54 kilonewton per meter. This is 1.73 kilonewton per meter. This is 4.44 kilonewton per meter. So you can see maximum force will be distributed to the lower reinforcement, and that is 4.44. So in the next class, what I will do, I will check that this reinforcement force that is developed, that is the tensile force that is developed 4.44 kilonewton per meter, that is the maximum force. So now that is the force due to the seismic effect, and then we have already the static, the tension force is developed due to the static load. So now we will add them and then we will check whether it is within the allowable value or not, because to incorporate that seismic force, I have already reduced the allowable T when I design it under static condition by 60%, or I have reduced it by 40%, I have taken 60% that. So now let's see whether it will safe or not. So that I will do in the next class. Thank you.